All right, open up your book to section 2-6. Section 2-6 starts on page 102 in your book. And the title of this section is Logarithmic Functions. The objective is to show that logarithmic functions have the multiply-add property and be able to find particular equations algebraically. So we've talked about the other four functions in this chapter and being able to do these things. We've talked about the linear, quadratic, exponential, and power functions. We've talked about their numerical patterns as well as their equations and being able to come up with those. And now let's take a look at the logarithmic function and see if we can do the same thing. All right, so the logarithmic function, the general equation of that looks like this. We have y is equal to a plus b times the log base c of x. And I know when you look at that equation, it looks like there's three unknowns in there because there's an a, a b, and a c. But it turns out really there's only two unknowns in there because of the fact that the base, the c in this expression here, is going to be either given to you in the problem or you're just going to be able to pick whatever base you want. So you won't have to find the value of c if you're trying to find the equation of the logarithmic function. A couple of values that we throw out here from this to eliminate the trivial cases. If b is equal to 0, then you just have y is equal to a. That's just a constant function, so it's not even logarithmic. We force c to be greater than 0. We've talked about the restrictions on the logarithmic function in the previous section, and we have to have a base that's positive. And it's not going to be equal to 0. Again, that comes straight from the definition of what a logarithm is. Otherwise, when you write it in that exponential form there, that's the base would be 1, and 1 to any power is 1. So that's the trivial cases that we throw out. So there is our general equation there for a logarithmic function. Y is equal to a plus b times the log base c of x. And now let's look at what the graph of a logarithmic function looks like. Turns out that there's a couple ways we could sketch this depending on the value of b. If b is positive, then that means that you've got yourself an increasing logarithmic function. It turns out that the y-axis is actually a vertical asymptote, so you'd end up with a graph that kind of does something like this. And you'd have a vertical asymptote right down here on the y-axis. That's what an increasing logarithmic function looks like. If b is negative, then that just is a vertical reflection of this. And that would be our decreasing logarithmic function, so it would look something about like this. And again, your y-axis is going to be a vertical asymptote. So there's a sketch there of what those might look like, two possible sketches of what your logarithmic function looks like, depending on the value of b. Let's take a look at the parent and transformed functions. Again, we've done this for each of the other four functions in this chapter. The parent function, if you kind of strip it down to just the basics here, it would be y is equal to log base c of x. That gets us a logarithmic function. So we've stripped away the a and the b there to get that. The transformed equation, if you take that parent function and now transform it, you'd end up with this equation here. B is a vertical dilation factor, so we can stretch this thing vertically by a factor of b. A is our vertical translation, and the d is your horizontal translation. So if you do a horizontal translation, just realize that's going to change the location of that vertical asymptote in that sketch, but as long as that's 0, then it's at the y-axis there. But there's our transformed function there for a logarithmic function. The last two pieces of information here are the domain and range. The domain there for a logarithmic function, we already mentioned this, and we've kind of used this as we were solving equations that involve logarithms, is the domain has to be greater than 0. X has to be greater than 0. You can see that from the sketches up above. And the range actually goes from negative infinity to positive infinity. It's all real numbers. Right, that vertical asymptote there along the y-axis keeps us closer and closer to that value, but it never touches the y-axis, so that's why it goes all the way to negative infinity. And this graph here, if you're looking at the graph on the left, that's the increasing one. It very slowly increases. It's from 0 to 1, it increases really fast. But then after that, it gradually increases. It slows way down. But it does go, in fact, to infinity. There's no horizontal asymptote up there. So that's our domain and range. Turns out that exponential functions and logarithmic functions are inverses. We used this property actually when we were solving logarithmic and exponential equations in the previous section. And it comes straight from the definition, by the way, is how we can see that these are inverses of each other. But it turns out that the exponential function and the logarithmic function are, in fact, inverses of each other. For example, if you take an exponential function like y equals 2 to the x, that we recognize as an exponential function. It's in the form of y is equal to a times b to the x. A would be 1, b would be 2. There's our general form there for an exponential function. If I take and swap those two, swap your x's and y's, that is, if you swap your x's and y's, you're finding the inverse. And if you swap your x's and y's in this case, you'd end up with x is equal to 2 to the y, which you might not recognize as a logarithmic function. But if you go back to our definition of a logarithm, remember there's two ways to write this. We say that y is equal to log base b of x, or that x is equal to b to the y. That's what we have here. I could also write this as or y is equal to the log base 2 of x. Those two things mean the same thing in red there, those two equations. So the first one probably that I wrote down, you probably don't recognize that as being logarithmic, but I definitely recognize that's the inverse of the exponential because I can see the x's and y's have been swapped. But if I write this second one here in the second form there with the logarithm, now I can see that that, in fact, using the definition of a log, is a logarithmic function. So those, in fact, are inverses of each other. I swapped my x's and y's, and I got the other equation. In fact, if you look at these graphically, in blue here we've got your exponential function, y is equal to 2 to the x. And in red we've got our logarithmic function, either x equals 2 to the y, or that's the same as y equals log base 2 of x. And you can see that if I draw the line y equals x through there, the line y equals x is in fact a reflection of the blue curve onto the red curve, or vice versa. So that's another way we can recognize that we've got an inverse if we've got symmetry across the line y equals x. And that's what we've got here. So your exponential function and your logarithmic function are inverses of each other. With that information, we can then start to relate some of the properties we know about exponential functions to logarithmic functions. All right. So since exponential functions and logarithmic functions are inverses of each other, we should not be surprised at this pattern right here that shows up for logarithmic functions. That is, we know that the exponential function has the add-multiply pattern. So if I swap my x's and y's, that add-multiply pattern must become a multiply-add pattern. And again, if I take an exponential function and swap the x's and y's, I'm finding the inverse. And the inverse we just stated was a logarithmic function. So again, this shouldn't be too much of a stretch for us to understand that the logarithmic function has this property of being multiply-add, or the multiply-add pattern. Take a look at the example that they give you there on page 103. If we look at this set of data here that they give us, or a piece of this data here, they gave us these values here that when x is 1, y is 6, 18, 2, and 54, 3, it looks like are the values they've given us here. And it turns out that this is the set of data that falls on some exponential function out there, some logarithmic function out there. And it turns out if you look at this set of data, that you'll notice a pattern. That is, if I multiply my x's by 3 here, 3 times 6 is going to give me 18, and 18 times 3 is going to give me the 54. That in turn, it turns out that I'm adding some constant over here to the y's. It's clearly adding 1 each time. There is our multiply-add pattern. So then the question becomes, can we actually show this pattern here? Can I show that if I take for this function, if I multiply each of the x values by 3, that it turns out that I'm just adding 1 to each of my y values. Well, we can do that, but in order to do that, I need to know what the function is that we're working with here. So let me grab this box out of the way. Here is the function they've given us here. That probably wouldn't have been your first guess as to what the equation was, but there it is. That's the equation that makes up this set of data here. Log base 3 of 0.5 plus log base 3 of x. All right. So can we show this pattern? And the answer is yes. We just got to go about the algebra to make that happen. So if I'm trying to show that f of 3x is equal to f of x plus 1. So f of 3x. Well, first start out by replacing the 3x, or sorry, the f with what it's equal to. F was this function up above here. So that's log base 3 of 0.5. Log base 3 of 0.5. Plus the log base 3 of x. Now that was because we were plugging in x. Here we're going to plug in 3x. So I'm going to add on the log base 3. Instead of x, it's going to be 3x, because that's my argument for f of 3x. All right, so now what we need to do is use a property here that we have for logarithms to help us show this property, because I want to get this in terms of just f of x. So I've got to break up the 3x over there that I'm taking the log of, is what I need to do. I'm taking the log of 3x. So one of our properties for logarithms is a product property. So let's use that. Leave the first part of this alone, log base 3 of 0.5. And then if you have the log of a product, you can rewrite that as the sum of the logs. So I can write this as the log base 3 of 3 plus the log base 3 of x. And now let's reassociate these terms here in the order that I want them. I want the first term, log base 3 of 0.5. And I'll take the last term there, log base 3 of x. I'll put those in parentheses because I'm going to put those guys together. And then the middle term is what's left there. I've got the log base 3 of 3, which actually that turns out to be a pretty nice number, right? Log base 3 of 3, I can do that without my calculator. But look at what the first part I have here that's in parentheses. That first part is just my original function. Log base 3 of 0.5 plus log base 3 of x. If I go back up here, that's the original function, f of x, that I've got there. So I can replace that with f of x. And again, the log base 3 of 3, that's like asking what power do you have to raise the base of 3 to in order to end up with 3, and that's 1. So there we go. We have that if I take f of 3x, it turns out that that's equal to f of x plus 1. So yeah, we can show that it has that property for this set of data. All right, so now the question is, can we do that for a more general sense here? And again, we can do that. It's just going to take a little bit more effort here. And I got to remember my algebra skills there, use my algebra skills a little bit more perhaps, but we can do this. That is, if I start out with the general equation there for a logarithmic function, a plus b log base c of x, can I show that it has the add multiply property? That being said, can I show that if I multiply this by some constant, multiplying over there, that I'm adding some constant over here? And the question is, what constant are you actually adding, first of all? Well, I guess first of all, show that it is a constant you're adding, and then secondly, what constant is it is really what I want to answer here. So let's see if we can actually prove this multiply add property and also find out what that add value is going to be. If I'm multiplying by k, what does it turn out I add each time? All right, so the place to start is kind of the ending value here, the ending point for this, that f of x sub 2 is where we want to start. That f of x sub 2 is what I'm starting with. I want to show that that's equal to f of x plus, or f of x sub 1 plus some quantity. That's what I'm trying to do, get there by showing that it's equal to the previous y value plus some number. So let's replace x sub 2 with what it's equal to. Look over in your x column to do that. If we take x1 and multiply by k, we get x2. So I can write this as k times x sub 1. And now it's going to follow very similar steps to the one that we just did there, except I won't have numbers in here that I'm working with. But we should still be able to do this. I plug in k times x sub 1 into the original function f up there. I'll have a plus b times the log base c of k times x sub 1. Again, I'm replacing the x with k times x sub 1 as my argument. And again, we're going to use our product property over there with that logarithm. So let's leave the a alone and rewrite this as b times, and I'm going to distribute that b through in just a second. So let's put parentheses here so I don't forget this. If I've got the log of a product, I can rewrite that as the sum of the logs. Log base c of k plus log base c of x1. And now let's distribute the b out front there through those parentheses. So it'll be b times the log base c of k and b times the log base c of x1. And now let's reassociate some terms together here. I'm going to take the first term and the last term. So I'm going to write it as a plus b log base c of x sub 1. We'll put that in parentheses. And we'll add on the log base c. Oops, I missed the b part out in front. Let me try that again. There's a b times this log. B times the log base c of k. And again, if you look at what I have in parentheses now, that's actually the original function evaluated at x sub 1. If I go back up here, my original function was a plus b log base c of x. That's when you're plugging in x. But here I've got an x1 in there, so that must mean I've plugged in x sub 1 into this function. Oops. So I've got f of x sub 1 plus this quantity, b log base c of k. And there we go. I've now proven that if you start out with f of x sub 2, that I can rewrite that as f of x sub 1 plus some number. Not only that, I can tell that what that number is. It's b times the log base c of k. So let's fill that in. B times the log base c of k is that key value there. And again, if you look at the part over here that involves just the x, it's this chunk right here, the part that's directly affecting the x. If I replace the x there with the k, we'll end up with this guy right here. That might be a hint that you can use to kind of help yourself remember what that quantity is that you're adding. All right, so let's try a couple of examples here. Look at example 1 on page 104 in your book. Example 1 there gives us, first of all, a set of data here. So suppose that f is a logarithmic function with f of 3 equals 7 and f of 6 equal to 10. All right. You can write it the way they've given it to you, but I'm going to write it in a table. I like seeing it in that form. It seems like a little bit easier way to work with this. So 3, 7 and 6, 10 are the two values they've given us. For part A, it says without finding the particular equation, find f of 12 and then f of 24. F of 12 and f of 24. Now the key here is that they told us this was logarithmic. If they didn't tell me it was logarithmic, then I've got some trouble here. I've got to figure out whether I've got what kind of pattern I've got here. But they told me it was logarithmic, so if it's logarithmic, this is a log function. And that means that we've got the multiply add property. Okay, so I can follow that pattern there to come up with this. All right, so it looks like over here for my x's, I'm multiplying by 2. And over here for my y's, I'm adding 3. So I should be able to get the values that they've asked us to find there. Multiply by 2 and add 3. So if I multiply by 2, 6 times 2 is going to be 12, and add 3, that's 13, which is the first value that they've asked me to find. F of 12 is 13. Multiply that by 2. 12 times 2 is 24. Add 3 is 16, so f of 24 is equal to 16. So there's the first part of this one. All right, for part B, it says find the particular equation algebraically using natural log. Now, sometimes they're going to tell you what base to use for your logarithm, like they did here. They said use natural log. And other times they're not going to say, and you get to pick then. This was part A. So for part B. So this one we got to use natural log. So our equation here then is f of x is equal to a plus b, and it's going to be natural log. So they already figured out that the base c is that number e of x. So again, it looked like there was 3 unknowns from the general equation, but there's really only 2. They're either going to tell it to you or you get to pick that base. All right, we're going to solve this the same way we've solved finding the equation of those other four functions at the beginning of this chapter. And that is, we're going to pick a couple of values that they've given us or that we came up with, plug them into this equation here, and find out two equations in terms of A and B, and solve that system of equations. So I'm going to just pick the first 2 points here. It doesn't really matter which point you pick, but I picked the smaller numbers to work with. So I've got 7 is equal to A plus B times the natural log of 3. So we've just plugged in the 0.37. And now take the 0.610. So I've got 10 is equal to A plus B times the natural log of 6. Now since I'm adding the A and the B parts together here in these two equations, now I can just simply use addition or subtraction here to eliminate a parameter. So I'm just going to subtract these two. So I'm subtracting this one, which means I got to distribute a minus sign all the way through here when I go to do this, okay? What do we end up with when we subtract this? Come on. 7 minus 10, that's going to be a negative 3. The A minus A, that's going to be 0, so that's going to drop out. That's my elimination. And then I've got B natural log of 3 minus B natural log of 6. All right, so let's factor out the B there over on the right side of this. Negative 3 is equal to B times the quantity, natural log of 3 minus natural log of 6. If these were nice numbers, you'd probably immediately just simply write down how many B's you had there. But since natural log of 3 and natural log of 6 are not nice numbers, I wrote it this way. And now I just have to divide by that difference there to solve for B, right? If actually, let me simplify this one more step here. If you've got the difference of logs, this is our quotient property. Natural log of 3 minus the natural log of 6, that's the same as the natural log of 3 over 6, or that would be 1/2, right? I can use my quotient property to come up with that. You don't have to do that step, but I'm going to simplify it there. So now divide by that quantity. We'll have a negative 3 over the natural log of 1/2 is equal to B. So there's our value of B that we should have. And now I can take that value of B and go back to either one of those two equations that I started with and come up with the value for A. So let's take the first equation here. 7 is equal to A plus B natural log of 3. And our value of B here is a negative 3 over the natural log of 1/2. That's times the natural log of 3. And so now if I guess I can add that quantity to the other side there since I've got a negative 3 in there to solve for A, it looks like. So A is going to be 7 plus the 3 over the natural log of 1/2 times the natural log of 3 is our value for A. I'd suggest we come up with decimal approximations for those since those don't look like nice numbers. Let's grab our calculator and do that. All right, so on your calculator, let's punch in the value for B. What do we come up with? Negative 3 divided by the natural log of 1/2. Oops, 1/2. There's our value for B. 4.328, it looks like, is the value that we should end up with there for our value for B. And then for the value for A, that one was a little bit more to it. It was 7 plus 3 over the natural log of 1/2. And we multiplied that by the natural log of 3. So we get 2.245, it looks like, should be our value that we have there for B. Let me grab a picture. That's the value of A. Let me grab a picture of that. Paste it in here. All right, so we can write down what our values are here on our slide. So our value for B that we came up with was, again, that first value, 4.328. And our value for A was 2.245. Again, make sure you answer the question that they've asked you. They didn't just ask you to find A and B from that equation, or from that general equation. They said write the equation. So your equation there should be A plus B times this natural log of X. So let's write it that way. We have 2.245 plus 4.328 times the natural log of X. There is our equation. Right, and then for part C, C says confirm your equation gives the value. Well, I'll let you do that. You can take that equation now, you can plug that into y1 on your calculator, and you can evaluate it at 24, verify that in fact you get the value that we got up above there was 16 is the value that we got above, I think. All right, let's take a look at the last example here. It says to plot the graphs of these functions and identify their domains. So for A says we have f of x is equal to 3 log of x minus 1. 3 log of x minus 1. All right, so let's consider the domain here, and that will help us sketch this. You could obviously grab your calculator and start sketching this, but let's think about the domain here, at least to help us start sketching it. The domain for this, if I look at x minus 1, what I'm taking the log of, that has to be positive. So that tells me that x minus 1 has to be greater than 0, so that means x has to be greater than 1 when I add that on there. So I guess I can actually write that over here. I've got my domain for this function is x has to be greater than 1, which was part of what they wanted me to do in this problem, was identify the domain. So I guess we did that. The other thing to note here is, I guess, a couple of key points that this goes through to help me sketch this. Remember that I guess one thing that I would look at is the x-intercept. The x-intercept, when you take the log of 1, you end up with 0. So whenever x minus 1 for my x-intercept, whenever x minus 1 is equal to 1, log of 1 is equal to 0. So if I solve that, I'd have x is equal to 2. So I should expect to see an x-intercept then at x equals 2 is where I should cross the x-axis. We already know you have a vertical asymptote at x equals 0, but we've actually shifted that function. If I've got x minus 1, think about the translation that's taken place here. The x minus 1 there, you've translated this thing 1 unit to the right. So instead of my vertical asymptote at x equals 0, I'd expect to see a vertical asymptote at x equals 1 is what I'm going to expect to see when I look at this graph. And if I want to have at least one more point here to plug in, then think of this base, since this is a nice base here to work with. This is a base 10 logarithm that if I take, for example, I'll just call this a point. We're trying to come up with a point that this goes through. I know that if I take the log base 10, or the common log of 10, then that's like asking yourself, what power do I raise 10 to in order to get 10? That's 1. Okay, log base 10 of 10 is 1. So that would mean that anywhere that the x minus 1 up above is equal to 10, that I could find out what the point that I'm going to. That is, if I look at this quantity right here and make that equal to 10, I should be able to solve that to find out another point. So if I take x minus 1, set it equal to 10, that'd be x equals 11. So I'm going to expect that at x equals 11 that I've got a y value of 1 is what that tells me. All right, so with that, I should be able to sketch this. And so let's see what I come up with here. Kind of combining everything that we just described there. I'm going to only focus on the first and the third quadrant, first and fourth quadrant here, because of the fact that we know it's only defined for x is greater than 1. We already figured out the domain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here's 11. 2, 4, 6, 8, 10, 11. So I can now mark a few key points here on my sketch. So we said that we got ourselves a vertical asymptote at positive 1, because we've shifted this thing horizontally by a factor, by 1 unit. And I expect that it's going to cross through at x equals 2 is what we said there is going to be our x-intercept. And then at x equals 11, I'm expecting to be up here at 1. So I guess I could have used a slightly different scale, because it's not going to go very far into the first quadrant with what I've got here. But this is the sketch that I'd end up with then. End up with something like that. Yeah, I probably should have changed the scale up here. Let me do that. Just be something a little better to look at. Let's make this be -1 and this be a +1. So now this will be up here. It's a little bit easier to sketch as well. Okay. there's what I expect to see there for that function. Again, you can grab your calculator and check it out, but you should get to the point where you're comfortable looking at the equation and thinking about the transformations you see there to come up with the equation, or to come up with the graph. All right, look at part B. B says we've got the opposite of the natural log of x plus 3. So f of x is equal to the opposite of the natural log of x plus 3. Again, think of your transformations here. The negative out front means that's a vertical reflection of this thing. So that's our b value being negative here. And the x plus 3, we've shifted this thing back to the left 3 units there. In fact, if you consider your domain, that'll help you see why that is. If you look at this part right here, our domain, that quantity, x plus 3, has to be greater than 0. So solve for x, subtract 3, which gives us x is greater than a negative 3. So yeah, instead of our vertical asymptote being at 0, we've shifted that back to the left at negative 3. And we're decreasing through here. So this is the negative out front. So we should be able to sketch this pretty accurately. So here's negative 3. So I'm expecting to see a vertical asymptote right here at negative 3. And I cross the x-axis whenever this quantity right here, my x-intercept, the log of 1 is equal to 0. So wherever that's equal to 1, x plus 3 equal to 1, subtract 3, we'll get x is equal to a negative 2, right? So I'm going to expect to see we cross the x-axis right there, and we can sketch what this looks like here roughly. We'll do something about like this, we'll say. Okay, again, you can grab your calculator and confirm that sketch is correct. All right, look at part C. C gets a little bit more complex because they throw a quadratic in this equation, don't they? They have f of x is equal to the log base 2 of x squared minus 1. Okay, so let's start with the domain of this thing. Remember, again, you got to consider where that x squared minus 1 is greater than 0. I guess you could do this one of two ways. You could think about what the quadratic function x squared minus 1 looks like and think about where that function is above the x-axis where it's positive. What domain do you get? You could also factor this. This factors nicely. X minus 1, x plus 1 is greater than 0. And that would give you 3 points on your number line, or sorry, 2 points on your number line to consider at negative 1 and at 1. And you could plug in values to the left of negative 1 and see whether you get a positive answer or not. And then plug in a value between negative 1 and 1 and 1 to the right. And that will help you see what the domain of this is. For example, if I pick like negative 2, when I plug in negative 2 minus 1, that's negative. Negative 2 plus 1, that's negative. A negative times a negative here is going to give me a positive answer. So it's going to include these values. It's going to be an open circle here, though, because I'm not including the negative 1, because that'll be equal to 0 there, but not greater than 0. If I pick a value between negative 1 and 1, like let's pick 0, for example. If I plug in 0, 0 minus 1 here would be a negative 1. 0 plus 1 is positive. So negative times a positive, that's not going to give me a positive answer. So it does not include this section here. Pick a value to the right of 1, like 2. 2 minus 1, that's positive. 2 plus 1, that's positive. A positive times positive, that's going to be positive. So it would look something like this on my number line there. In other words, I'm going to end up with x is less than negative 1, it looks like. Or x is greater than 1 is my domain here to consider. All right. Now the other thing to note here on this one, it's quadratic like this. If I were to look at what f of negative x looks like, if you plug in a negative x into this, you're going to end up with the log base 2 of a negative x squared minus 1, which turns out to be the log base 2 of just x squared minus 1, right? You should go, oh, that's the same as f of x. So it turns out that that f of negative x is equal to f of x. And again, you should be thinking about some of the properties we talked about in the last chapter, but that's what it means to be an even function. So there's some symmetry across the y-axis for this thing. So with that information, I should be able to sketch what this thing is going to look like here. Again, you can find your x-intercepts and things like that too. We'll help you with this sketch, but I think we got enough information here to help us sketch this. If the domain is from for x is less than -1 and x is greater than +1, here's -1, here's +1. That means that we're excluding this interval between -1 and 1, so there's going to be a vertical asymptote on either side of this. And there's not a negative sign out in front of my logarithm there, so it's an increasing logarithmic function. So it must look something like this over here, and because there's symmetry across the y-axis, it must look like something like this over here. That's our sketch of what this function must look like. All right, that's all we need to know there from section 2.6.